Hi, welcome to lecture 8, I think. This is on the derivative as rate of change. You may notice that it looks a bit different, sounds a bit different. Yes, I'm using new software, a new setup. This is considerably simpler, but it still has a few glitches. We'll see what it finally comes out looking like. So we've been talking about limits, and now it's time to move into the main event, which is the idea of the derivative. The derivative is at the center of all calculus. The derivative is what measures change. We've already talked about change as the quantity that requires us to hold two things in our heads at once. We have to think about the change in one thing relative to the change in something else. I used an example of salary, for example. And if you talk about somebody's salary changing, it's difficult to just say, well, my salary went up by $100,000, but you also have to know what time is involved. Well, we'll see that there are plenty of examples like that where time is the independent variable, and then the dependent variable is something like money. But as we'll see, there are plenty of examples where you can have any variable that you like dependent on any other variable. So, even learning could be dependent upon the number of people in the classroom. You might decide to find some sort of relationship like that, some sort of function, and then ask the question, what would happen if I change the number of people? How much would that affect the learning? So that's kind of at the heart of this change idea, that we have a change in the y value based upon a change in the x value. And what we've been able to do so far is look at the notion of the average rate of change. And that's just the difference in the y values divided by the difference in the x values. We saw an example of that where we were driving from Valparaiso to Merrillville, and we had a notion of average speed. But the problem with that is that it's just an average. It's over a long period of time. And as you can tell, if you were really doing that kind of situation, driving from some point in time to some other point in time and plotting your distance this way, then if you were looking at this kind of curve, you can tell that when you're in this part right in the middle, sort of, you're not moving at all. Maybe you're stuck in traffic. And then here you're moving very fast because you're covering more distance over a short period of time. And what we'd like to be able to do is capture this idea of what's the instantaneous rate of change right at this point. How fast are we going right there? And obviously at this point we're not moving very fast at all. So how do we determine those answers to those questions? And it turns out that we can use limits to do that if we're somewhat careful. So that brings us to really the kind of definition, but I'd like to motivate it with a picture. Let's make it a little bit simpler. Let's suppose that our curve looks like this. So this is our y. That's going to be a function of, let's change it to something that's more familiar to everybody, just x. And we'll keep it simple. And what I want to do is get an idea of what the rate of change would be at a particular point A. All right. Now I could do an average rate of change. I could go from A to some other point, like A plus some number h. And then at each of these points I could go up to the graph of the curve and plug in those 2 points and get the y values. And so then I could calculate my delta y over delta x, and of course that's the average rate of change. But what I'm interested in is what's happening right at A, what's happening here. And to get at that answer, I could think of asking the question, what happens to this point as h gets closer and closer to 0? What if I took a limit of something as h goes to 0? That would make this a plus h point kind of slide in towards a. And simultaneously, it would make the point that's up here on the curve slide down all the way to the point a f of a. Right? But that's not all. At the same time, each of the delta y over delta x quantities that's being computed would change its value also. Each of the average rates of change would change its value. Now, let's look at this picture one more time, only this time I want to look at that average rate of change again. And you've seen this before, but I just want to make sure that everybody is aware of it. If I go from A to some other point, which up above I'm calling A plus H, and just calculate the delta y over delta x, and if this function is f, so y equals f of x, then I could write this average rate of change as f of a plus h minus f of a all over h. Well, I'm cheating because I already computed the distance from here to here. It's the change in y, that's the change in the y values here, which is this one minus this one. So that corresponds to the length of that segment here, the vertical segment, f of a plus h minus f of a. And then I have to divide that by the difference between a and a plus h, which is just a plus h minus a. And of course the a's are going to cancel, and that's where I got this h from down here. So this quantity that you've seen before, we call this thing a difference quotient. And it represents the average rate of change. No surprise. But what's new here is that if I think about letting h go to 0, maybe this difference quotient has a limit. And that limit would represent maybe the instantaneous rate of change. But what does it represent on this picture before I take the limit? Well, that's pretty easy to see, because if we think about the difference in the y values as being this number, and the difference in the x values as being this number, it's the change in y over the change in x, which is just the slope of the line that connects those 2 points. So you think of a line that connects those 2 points. Now, this picture isn't real good. Let me zoom in a little bit. There's a curve, and then there's the 2 points, and the line that I just drew actually is more like that. Right? It's not the curve. Here on this picture, the line and the curve look pretty much the same, but they're not. I never meant that to happen. The line is one thing. It's connecting the 2 dots, but the curve does something else. It's the slope of that line that is this difference quotient. So when you calculate the difference quotient, you're getting the slope of the line connecting the 2 points that have x values a and a plus h. All right, let's do this again, because I find the a and the a plus h kind of difficult to deal with. But we'll come back and use this in just a few minutes. I'm going to do it again with slightly different numbers. This time, same kind of picture. All right. I'll have my a here, but instead of choosing this instead of choosing this point to be a plus h, I'm just going to call this x. And I want to think about x as sliding into a all by itself. All right? And it's the same picture. You've got a point up here on the graph of f. You've got a point up here on the graph of f. And your delta y over delta x is still going to be the difference in the y values divided by the difference in the x values. But in this case, the difference in the y values is a little simpler. It's f of x, whatever that is, minus f of a, divided by the difference in the x values. Now nothing cancels. So you might say, well, why do I want to use this? Well, to me, this makes a lot more sense, because I look at that thing and I say, oh yeah, that's a slope, obviously. I obviously see a change in the y values on top divided by the change in the x values on the bottom. And this difference quotient, this also is a difference quotient. that difference quotient represents the slope of the line that connects those 2 points. So this m is exactly that. Okay, that shouldn't surprise you. But the question is, what's going to happen when you make x slide in toward a? You can see that this point is going to slide along the curve, but every time you move this point down the curve, you're also getting another line connecting those points. So I want you to imagine these lines. Every one of those lines will have this point in common, but they're going to be coming in like this, maybe. And they'll all have their own slope. And maybe those slopes have a limit. And then we're going to calculate it. The limit in this case, not as any h goes to 0, but as x simply slides in toward a. And this would be f of x minus f of a over x minus a. So that's the quantity that we're after. This quantity is going to be, we hope, the instantaneous rate of change. Now, let me back to the other one. The other one was very, very similar. The only difference was instead of x, we made it a plus h. So it really doesn't matter in the grand scheme of things. Sometimes one of them is easier to understand than the other. In this formulation with a plus h, you're going to write the limit as h goes to 0 of f of a plus h minus f of a over the difference in the x values, which just reduces to h in this case. So here's the thing. If you're looking at this formulation, you're thinking about another variable besides a, maybe besides x, which has nothing to do with the point A where the action is taking place. It has to do with h going to 0. So h is kind of like a distance away from the action point, and you're saying that h value goes to 0. Here, you're focused on an x which is sliding into a. So I can say that, I like this one better, but honestly, I end up using this one at least as much. So you really have to get used to both of them. So what are these? These are both expressions of the instantaneous rate of change. They both are the instantaneous rate of change, and they are the instantaneous rate of change at the number x equal to a. Now what if you wanted the instantaneous rate of change somewhere else? What if you were interested in the instantaneous rate of change right there, for example? Well, then you'd have a different a. And obviously, if you play this game and calculate the limit, the slopes are going to be somewhat different. And in the end, you may find a slope of a line as a limit that is something like that. Well, that's exactly what you want. You want to calculate the instantaneous rate of change based on where you are. So the summary of all of this is we calculate a difference quotient as a difference in y values over a difference in x values, where we allow one number like x to change and slide in towards a, or we allow this one number h to get smaller and smaller and smaller. And so what we have to do is calculate that difference quotient, calculate the limit of that difference quotient, and what we get is the instantaneous rate of change. Now the instantaneous rate of change has a name, and that's what we call the derivative. So the derivative is the instantaneous rate of change. It is the limit of the difference quotient, however you express it. And in both of these cases, either one, we have a special notation for it. It's related to the function f. And what it's called is f with this little kind of a hash mark. It's not an exponent of 1. It's kind of a diagonal hash mark. But we call it f prime. Nothing to do with prime numbers, f prime. But this is the derivative, and it's the derivative in this case where? Where the action is located, and that would be at the number A. Now, a little bit later, we're going to ask the question, well, can I do that at all possible A's at once? It turns out the answer is usually yes. Yes, I can, but we'll worry about that a little bit later. Okay, I'm going to call it quits for this particular video, but I want to do a whole bunch of examples, and I'd like to do them separately. So let's make sure that you take a look at the other video for this coming Monday as well. All right.